And this is that big game that I was talking about called Idle Horizons, which is super addictive. So I don't recommend you to download this, but it's a lot of fun. So you have like a lot of different heroes where you get different weapons, and yeah, you fight each other and so on. And that's the one with I think 80,000 monthly active users. And this is another of my favorites. It's a rock band called Gigabull, and every time they release a new song from the band, they make a new level, and you kind of like play the song to the level, which is quite creative. Let's see what we have here. Here is one of the first Flame games that went popular. It's kind of a puzzle game where you're spinning around these mazes and you have to like watch out for the skulls and get all the coins. And there are lots and lots of these type of like casual, easy games where it's just, yeah, something that it takes you like a day to write, but if it becomes popular, you can earn quite a lot of money on it anyways. Wow, I had a lot of videos in here. Oh yeah, and now recently we got shader support from Flutter, so now you can do these cool shader techniques. I think it's pretty hard to see it in here, but it's like a lot of glow there and reflections in the water underneath and things like that. So if you're if you know what shaders are, it's, you know that's quite a powerful tool in game dev. And a lot of people ask, so what about 3D? And like, if you want to build a big 3D game, I would not recommend Flame. But we have built a package now called Flame 3D, because Flutter is getting some initial support for 3D. So you can build games in 3D, but if you want to do that, I would recommend you to go to like Godot, for example. But you can see that it still works. Like you can use your 3D models and run around in a 3D space. All right, that was it for my presentation. Do you have any questions? Thank you. So I'll swap over to this mic then.
Thank you. Thank you for the awesome presentation first. I wanted to ask, so is there a reason why I would use Flame instead of Unity? Is it just because I know Flutter already, or is there another reason?
So if you've used Unity before, it is kind of, like you can get it out. Feels like we're getting some echo here. So you can deploy it to most platforms, but it is much harder than it is in Flutter. And you also have so many more debugging tools in Flutter for running on all platforms at the same time. Like you can have a bunch of phones laying on your desk and it automatically updates when you're doing that. And a lot of people that choose Flame too, I mean, firstly, it's open source and completely free, and you don't get screwed over by some crazy licensing team at Unity. But Flutter is, or Flame is like code first. So if you really like coding, then people usually feel more at home with that than doing a lot of things inside of an editor. But obviously, like, yeah, for building big games, bigger engines like Godot or Unity is a much better tool to use.
Yeah, thank you. Just one more thing. I don't know. I haven't researched Flame, so I really don't know the capabilities it has. But would the game developed in Flame be performant, just like any other game?
I mean, it depends on what type of games you're building. So I think like this, what is it called, Bullet Hell game there, I think at some points they have like thousands of enemies on there and it's still performing. But when you get to having lots and lots of things on the screen, you also have to start thinking about performance. because you can definitely run into performance troubles, absolutely.
Yeah, so I was noticing based on the examples, most of the games were sprite rendered animation games, and I was just curious about how extensive is the support for GPU rendered, gaming, and how well is the support for rendering games with GPU, and how a low level or native APIs can you use, directly from, depending on the platform. In this case, Flutter is cross-platform. So how extensive is basically that support there?
Great question. So Flutter under the hood is using the GPU a lot for the rendering, but a lot of the time, or not a lot of the time, but if you want to do some crazy things directly on the GPU yourself, there is a package called Flutter GPU, which is also what we're using in our 3D thing. And that one, you just feed it like GLSL things or so, and it handles all of the underlying GPU protocols like OpenGL and Vulkan and stuff. But it's still very early stages for that package. They're actually thinking of doing like a web GPU implementation also. So yeah, there's a lot of things happening in that space.
Great, awesome, thank you.
Thank you. Okay, any more questions? There's one more there.
So my question is about the multiplayer platform. Does Flame provide something that handles the heavily connection synchronization if somebody wants to build a multiplayer platform game?
Yeah, so there are lots of different options there. So a lot of like multiplayer servers that you run, they're like kind of agnostic to what engine you're running underneath. So you could use something like Nakama, for example, if you want to have a lot of like real-time updates going out to all of the players at once. But if you have some more casual game, I would recommend using something like Supabase, or there is a Dart backend called ServerPod, which is quite nice too. But Flame doesn't have any like net code built in at all, but it's usually quite easy to integrate with these like engine agnostic platforms.
All right, so I guess that's it in terms of questions. So big applause for Lucas. Thank you very much.
Thank you for having me. And I guess the workshop starts in half an hour?
Yeah, so there's a workshop that's coming on room 1, which is on the back on the left. If you want to attend Lucas' workshops on how to build games.
And you don't need
Flame.
any experience at all before it, but try to install Flutter on your computer before you come there, because it can take a little time to
prerequisite,
download
install Flutter, and make sure to attend the workshop in half an hour. All right, thank you very much. So next onto the stage, I'd like to invite Senior DevOps Engineer and also Professor, Teaching Assistant at FIAC University, Flaka, who will we welcome to the stage with a big applause. And who's going to be talking about moving from detection to prevention with AI in cloud security. Do you need this one or
Rizarda.
Rizarda. I don't know where that name. I guess from the Flames.
Maybe. Okay, so hello everyone. I'm very happy to be part of SFK 2025 as a speaker today. For you who don't know me, I'm Rizarda Thaci. I'm a teaching assistant at the Faculty of Electrical Computer Engineering at the University of Pristina. At the same time, also a PhD candidate and also senior DevOps engineer. What I'm going to present today as I think is a very interesting topic nowadays that has to do with artificial intelligence, or AI as we know, is that how this AI shift has been in the cloud security area, starting from the detection part until the prediction one. So I'm going to talk about how cloud security is being transformed from reactive responses to proactive intelligence. So how is this proactive intelligence? We're going to see on the next slide. Let's try to do a comparison with the traditional security methods that we have been using from the past until now, and what is the difference between the AI methods during the different processes for threat detection, especially in cloud environments. So how we all may know AI, one part is from ChatGPT, from DeepSeek, and other different platforms that are for AI. So how we really know AI is that it is only like a chatbot generating human-like text, or like, for example, a conversational interface. It is a creative writing assistant, or a virtual personal assistant, and so on. But we will show now how AI is much more and how it is different in different fields, and especially in the cloud security area. So AI, or artificial intelligence in cloud security, is very different from how we have been starting to use AI from the beginning. So if we look at the cloud security area part, we will show how AI is like a more sophisticated listener for different things, like for example, for analyzing system logs, network flows, or also IAM calls. So for example, let's say we have a cloud environment and we want to predict something. We want to predict a threat or attack that is being in our cloud environment. So this is where AI has the main role in this part. The second one, how it does this detection before the threat comes into our cloud environment, is like detecting patterns before they even become incidents. And this is done through the prediction part, which in the next slides we're going to see which are the main steps of how AI algorithms do this prediction before an incident occurs in a cloud environment. And also what it uses to identify what data it uses and what are the test cases towards the cloud environment, and not only. So let's talk now how this AI shift has been done from the detection to the prediction part, that is quite redefining also what cloud security means in reality. So why traditional detection fails? Like until now, we know that many companies are shifting to cloud, and now all of those traditional methods we have been using are not as much effective anymore because of the many changes that have been happening in the cloud environments, and also the evolving of the different threats and attacks that are towards the cloud environment. So that's why I'm going to tell you what are the three main things why the traditional methods maybe fail on the detection part of different threats and attacks. So the first one, the static alerts. In the previous slides, I have been talking about how only after an incident we know if our cloud environment has been attacked or not. So let's say we have an AWS account and we have like configured different alarms or CloudWatch alerts in our environment that could tell us whenever a threshold is crossed or whenever something malicious is happening in our account. So what is the main problem here is that after an attack is in our cloud environment, we get an alarm that our environment has been attacked. But at the time being, the damage has already been done. So we haven't prevented anything for the attack to not happen in a cloud environment. So what happens is that it prevents all this proactive defense against rapid moving threats, and also about many different threats that have been known before in cloud environments. So let's say we have a DDoS attack, an MITC attack, but if we have another attack that hasn't been seen before, then through the static alerts and also from these traditional methods, we won't be able to know that we're being affected in a malicious way in our cloud environment. So what is the second part? Is the signature-based rules. So what are these signature-based rules? Is that are very effective when it comes to known threats. So let's say that our cloud environment knows that we're being attacked from a DDoS attack. So if we use signature-based rules, so we can know really that the DDoS attack is happening on the cloud environment and will be very effective to prevent it in the future. But when it comes to different threats, for example, zero-day exploits, or also novel attack vectors, MITC attacks, or maybe many other different attacks that hasn't been used before in the cloud environment, we would see that the signature-based rules won't be much effective as it should have been if we were using AI. So what it does in this case is that it creates critical window of vulnerability until the signatures are created. So first, if we have an attack, a signature is created, and until then, the attack has already been happened. So we still didn't prevent anything in our cloud environment. And also, it's very problematic if we have a cloud environment landscape that is going to be much different and much complicated in the future. And the third one that I think for many companies that still are using traditional methods is a very big problem. That is the human intervention. So let's say that we have a very complex cloud environment where we have a lot of logs coming on, like for example, millions of logs or thousands of logs that come in a time of seconds per hour or per milliseconds, just in case. And it depends also on the size of the cloud account that we have. What happens here? So we would need to have like a security analyst or a different employee that would have the role only for analyzing all those thousands and millions of logs just to see what happens in the case if we see something malicious. So what this leads to? It leads to alert fatigue and also to delayed responses. All those responses that we could have been connected or to have been gathered from AI, if we do this from the human intervention, it would be like for a lot more hours, and at the end of the day, we wouldn't find anything effective. And all these critical threats would be missed and addressed very slowly in this case. So I mentioned earlier that AI does the detection part through prediction. So we're going to show three main layers that AI goes through until the prediction part. So let's see AI as a nervous system that has like three main layers that it's going to use. And let's say that is constantly monitoring, analyzing, and reacting to the dynamic environment that we have in cloud, let's say in AWS. So what AI does first is the sense part. What is the sense part? It's first, before continuing to the prediction part or the training the model, etc., the main step here is how to prepare all the data in which this model will be fed or created in order to have much precise detection in this case. So what it does, it continuously ingests data from different cloud sources or also from our sources itself. So let's say that we have a lot of logs that we have been monitoring in the past, and then we can use the same one to create all the data that in the future is going to be used by this AI model that will be trained. Like for example, metrics, logs, events, and also this will be used for this real-time pulse of cloud environment. Like AI creates like a snapshot or a screenshot of how our cloud environment has been until now and how it is at the moment that it's doing the prediction with this model that we are creating. So let's say that we collected all those logs, we have all the data, and now the second part is to do that training of the model. That is the understanding part. So AI first needs to understand what this data is and what it can do with this data. So what does it do? It's like in the AI part, we have also a lot of machine learning models or algorithms that can be used for this prediction. So let's say random forest, SVM, gradient boosting, etc. And let's say that we are trying to train or to make the machine learning algorithm understand what data it has in order to create that training model that we're going to use for prediction. And then we can transform all this data into whatever we want to do. Like for example, if we want to detect DDoS or MITC, we can train the data in this case to detect DDoS. For example, if we have some parameters that are going to be used for DDoS attack. Let's say we want to know the IP address that is from the source or the destination part, or if you want to know for DDoS what is the time of the packets that are going through the cloud environment, and those will be the parameters that will be in consideration at the time that we want to train that machine learning model. So let's say that we have random forest, we have 3 random forests, and as such, we have created a model that is going to be used to do that prediction part of that DDoS threat in this case. And the third part is this prediction part. Let's say that we created the model, we have made the prediction, and now we know that, for example, our DDoS environment is being attacked by a certain threat and so on. So what AI really does, like for example, there are many use cases. If we want to automate this response or this mitigation action. So what is the interesting thing here in AI usage is that if we predict a threat, and now we know the reasons that the threat has happened, or if we want to do this mitigation action, is that for every part, if we have something malicious, we can just block it. For example, if we have a cloud environment with a DDoS attack, and we don't want to make much harm and to prevent not happen in the future, we can just put a filter that you could block all the other threats in the future that are DDoS or that are similar to that one. So what we have, traditional reactive detection only after incidents occur, whereas with AI, we would have proactive prediction and prevention for all those malicious things in our cloud environment in the future. So if we do a short comparison between the traditional security methods and the AI-driven security, I will start first with the alerts part. We saw the traditional part that all the alerts or alarms are triggered only after the incident or only after the attack has happened into an environment. Whereas if we see the AI-driven security methods, all the threats are anticipated or are detected based on some anomaly patterns based on the kind of the threat that is happening. And the detection is before the incident occurs, so before the attack is happening in our environment. It's like predicting if we would be vulnerable to certain kinds of attack in the future in our cloud environment. The second one, the traditional security methods, I have mentioned that there are lots of human interventions, like analyzing logs, metrics, and so on. Whereas when we have AI-driven security methods, we have real-time graph-based correlation, and this AI model that we are being created correlates all the behaviors between users, regions, or different services that are currently being attacked or threatened by something. The third part is how this response is made. We saw the previous slide that that AI does this response in an automatic way that learns and improves with different threats. So at the moment that it detects something, it just learns from those data so it can be trained to detect also other kinds and not only the one threat that is happening. And the fourth point is the number of logs and how those are being analyzed. So we know that there could be thousands or maybe millions of logs per minute, per second, or per hour. With traditional security methods, the processing speed is limited by human capacity, whereas at the AI part, the decision is made in a very fast time, like in milliseconds. And the AI processes all those vast data streams in real time every time that it gets new logs from different behaviors. So instead of waiting for different thresholds to be crossed, like for example, for the CPU spikes, if we have a traditional security method, predictive models it is learned what normal or malicious looks like, and it prevents the things even before it happens in the environment. So how prediction beats reaction? Let's say that we have a scenario in our AWS account, and we have an institute instance, a simple institute instance, where we have a lot of outbound connections, we have a lot of logs coming on, network flows, etc., in a very rapid pace. So let's say every 12 milliseconds or even every 6 milliseconds. And now what happens is that if there has been a human intervention here, the connection frequency is far too high for any human security analyst or for any human employee to analyze and to effectively detect what is happening in our cloud environment. So here's a comparison of the response time between the AI model and the traditional alert. So let's say that's the time span of 10 seconds. Like for AI, we can see that we can take the mitigation or the detection part with between 1 to 2 seconds at most. And the traditional alert, it would wait until the attack happens, and then it would create an alert for us that something malicious is happening at the moment. So if we go with the traditional approach, we can say that alert is logged after 50 minutes, for example. Then the alert answers the queue for human review, and also a significant change or damage likely has already been done in our environment. At the AI part, let's say that we have an LSTM model. Like, for example, that is one of the algorithms that are being used in deep learning, neural networks, and also machine learning. And what that does, that automatically triggers this mitigation, like, for example, on the VPC level, and also blocks this malicious traffic that I've been talking about from the previous slides in 1.2 seconds, or based on the threat is being currently in a cloud environment, to specify in what period of time we could block this malicious traffic towards our EC2 instance that we have in this case, in this scenario. So what AI really gives us in this case that also addresses this autonomous security effectively, at first is good to know that AI maybe can replace in the future many things, but still we just have to mention it or to know it just like an infrastructure that it defends itself based on the prediction part and many different parameters that it takes into consideration. So if we have to look at one of the things that AI can do is these AI feedback loops. So what is this? We saw the previous slide that we have different data ingestions in order for our models to be trained or to learn new threats that may be in the future. So that's what AI feedback loops is. So it continuously learns from different incidents, different threats. It improves prediction accuracy based on the data that it gets, and also is adaptive to threat modeling based on different threats that it gets in the environment. The second one is adaptive security posture. So what this really is that what it really helps is the policy agent part. There is the open policy integration agent, real-time policy adaptation, and also automated compliance verification every time. And the ML-driven drift detection. So not only to prevent the threats or so on, but there are many cases that AI can be used, like for detecting different misconfigurations in our cloud environment, not only for threats and attacks, but also for different misconfiguration or unauthorized change detection, automated remediation workflow, that this also can prevent any type of attacks. So if we take MITC threats, we know that one of the main parts that is being detected is this unauthorized change detection that has to do with this ML-driven drift detection based on the machine learning algorithm we have been using. So let's say we have a DDoS attack happening in a cloud environment that is a distributed denial of service. Let's say that we have an attacker. What DDoS does is that it tries to overload the traffic with a lot of bots, with a lot of traffic. Let's say that this part of the middle, or a large number of bots, let's say 100. And at the other side is a legitimate user or a server or a cloud account that is being like threatened or attacked at the moment. So if we could have been using traditional methods in this case, we would be notified only after the DDoS attack has happened, the server is down, and then there is nothing we can do to block or to prevent. So I have shown a simple implementation of how AI can be used for this detection of DDoS. So let's say that we have a random forest classifier that is one of the most popular machine learning algorithms that can be used for different types of detection. And what is the first step? Let's say that we ingested all the data, we loaded the data sets, we cleaned the columns, names, and also we removed everything unnecessary that it wouldn't help us in the production process. What is the other part is the data splitting. So this part is dividing data into training and testing sets that will be used for training the model. That is the first step, model training. And that initializes and trains this random forest classifier with, like, for example, let's say 50 trees. And then it makes the prediction on this test set and then calculates the performance metrics. So what are these performance metrics? We have accuracy, precision, recall, and F1 score. So if you look at the accuracy part, what accuracy really shows us, you can see also the part of the code that I have here. After we do all this training, prediction, and so on, these metrics are calculated, like this accuracy part. It tells the proportion of correct prediction, precision, true positive rate amongst positive prediction. Recall, we have the true positive rate among actual positives, and for the F1 score is the harmonic mean of precision and recall. And all these key metrics values tells us of with what accuracy this prediction with random forest classifier would be made for the DDoS attack that are currently being used for this implementation. Except of random forest, there are also a lot of different machine learning algorithms that can be used. Like, for example, neural networks or SVM and anomaly detection, and all of these have their different use cases, strengths, and description. So if we see at the use case part, so if we want to have an effective way for classification of network traffic patterns, as we had for the DDoS attack, the random forest has been told that is one of the best algorithms to be used in this case, because it also have like high dimensional data, it reduces overfitting, etc. So if we go to the neural networks, we can be using this if we have like the chance to detect complex non-linear relationships in traffic data. For example, if we would like to use this in the DDoS attacks, and we want to analyze all this traffic data, the relationship between each other, we will be using neural networks, because it also has high accuracy and adaptive to new patterns of that threat. Or SVM and anomaly detection. These are two other different kinds of machine learning algorithms that can be used, like, for example, for classifying traffic as benign or malicious based on different features, to have real-time processing, and also zero-day attack detection, or also if you want to be memory efficient in this case for the DDoS attack detection, but also for all the other different threats in our cloud environment. So what we could really do, like AI plus this human that can create this intelligent defense. So what AI really does, from what we can take from all this presentation, is that it's very good in automating different tasks to analyze a lot of data sets with different data beyond the human capacity, and also to predict threats before they actually happen in the environment. And also, if we would have the human strategic insights, we could design these intelligence systems together with AI to provide strategic oversight and also to shape security objectives and policies, and also to detect all those different kinds of misconfigurations, threats, and attacks toward any cloud environment, AWS, Google Cloud, Azure, and many others. So thank you for your attention. If you're interested, you can follow me in ResearchGate or Google Scholar and IEEE, when you can see some of my papers that is regarding the DDoS detection and how artificial intelligence is really being used to predict these threats in a cloud environment. So if you have any questions.
Thank you so much for your presentation. It was amazing. Given the October 20th AWS global outage that was due to a DNS attack throughout the industries and everything, so how specifically does the AI and the machine learning environment go throughout detection to prediction in this case? What lessons did we learn from this attack?
Okay. So first, before going to the prediction part, the main process here is to train that model as much as possible with different data. For example, if we would like to prevent this outage in the future DPS, we can use all the data that have been collected at the time that the damage has been done, so that the model will be trained and learning from all those outages, all of them different malicious traffic, so in order to do that prediction in the future. But also the main thing here to do the prediction is to know carefully what models should we be using, because the precision and accuracy should be as much higher as possible so we could have better results.
Thank you. There's one more question here.
Thank you very much for the presentation. Okay, that's very loud. So a lot of the problems sometimes with cybersecurity is that having closed source systems, they also have a lot of closed source data, and then a lot of the logs you will never get. And because if you get them, that would mean exposing company value or whatever. According to your experience so far, is it the open data that is already there and the models that are built on top of those, do they tend to give you a good enough standard, or do you really have to add more information that are so much more adapted to the company? So how good is the ecosystem already of open data and open models for this? Or do we have to really build everything ourselves when we're building this?
Okay, that's a very good question, because before we decide what data to use, like for example, there are many open source data sets that maybe we wouldn't know if they will help us much. So the first thing is to like see what are the most safer resources, because there are many websites that are from OSINT or etc. that provides a lot of logs that have been collecting from different testings. But from my experience and also from my research that I have been doing, that even if I took, like for example, different data from different open sources, I just try to reproduce my data myself. So for example, by analyzing all those logs that is towards my cloud environment, so I could use them on the future.
All right. Any more questions? I think time's up. So if there's any last question, I think that's not. So thank you very much, Razarta.
Thank you very much.
Big applause. Super important topic to cover. So before we go to the coffee break, I would like to invite to the stage Menan Selimi to talk about really interesting topic. And my challenge to you is, do you know what blockchain is? Raise your hands if you do. Okay. Are you able to explain blockchain in one sentence? Not really. Anyone? No? Guess not. So let's see if Professor Menan can explain blockchain in one sentence to us. All right, we're almost there.
Oh, perfect.
Perfect. All right. Do you need static or?
No, I have it. Yes, I will. Yes. So, hi everyone. I'm Menan, and I'm a professor and researcher working at the intersection of distributed systems, open technologies, and AI. My research focused over the decade, this last 10 years, I would say, has been focused on how to make communities install and apply these digital infrastructures. When I say digital infrastructures, I mean protocols and different type of services that they make them resilient and at the same time fault tolerant, right? So today I would like to take you on a short journey through three powerful ideas, which I believe they define the future of open source technologies. So I will talk about mesh, I will talk about chain, and I will talk about brain. So I will talk about how we make communities connect, why we need connection as a baseline in our life. Then I will talk about how to make these networks sustainable. Can we use blockchain to make them sustainable? And the last part will be focused on how we can bring intelligence, which I call edge intelligence, and how to make the system collaborate and cooperate with each other. So this talk, it's not just about technology, it's about, I would say, reclaiming control and how we connect, reclaiming control on how we collaborate, and reclaiming control on how we bring intelligence at the edge. So most of the things that I will say here are based on my previous research and studies done at the many different EU institutions in the last 10 years. So I will start with the first part, which is mesh, and I will start what happened with the community networks. So this was in 2013 when I joined the Polytechnic University of Catalonia in Spain for my PhD. So when I went there, I had to see that there you can find some of the really fascinating kind of like solution which they call wireless community networks. So what are these? So wireless community networks are self-organized networks which are built and maintained by their own users. So I would say different from the traditional or business-focused model used by the telecom operators in our region. These networks are owned, basically, and maintained by their own users. So no telecom operators, no IPCO, no VALA, nothing. So, and they became super powerful. Why? Because telecom operators, they couldn't risk going into a location in the villages where they didn't have financial incentives, right? So, and team of people, they came up and they invested, they bought the hardware, and they would just share their bandwidth with the others in order to connect to the internet. So the main motivation behind this network was internet connection. So one of these really successful effort of such kind of network is called GIFI, and GIFI it's considered to be the, I would say, the biggest wireless community network worldwide, which is located in the region of Catalonia in Spain, and it is really, really big. More than 37,000 nodes are in the network, and more than 100 people are using free internet access. So who is paying for the internet? Yeah, there are people which would pay for the internet, and they would just share their bandwidth with the neighbors. So it's a huge, it's a really fascinating network which grows very quickly. In a week, about 30 new nodes are installed each week, and this is one of the really fascinating stories and how people and communities are building this kind of networks. So even in terms of the traffic, I mean, the traffic every year is tripled. And here you can see, for instance, that the traffic to the internet has tripled over the past 2 years, and as you see here, the spikes, these spikes are the El Clasico games between Real Madrid and Barcelona, because people are streaming to their neighbors, and they would just bump up the traffic. So, well, these networks are super diverse. They use different routing protocols. They use different software, hardware, off-the-shelf hardware. Everything is like super, super open, even the hardware, even the software. And what is really fascinating is because you would end up seeing people, lawyers, that they know more about routing protocols than you. And this is what is happening. That's why they keep alive this type of networks. And here you would see like some kind of nanostation devices, which we say, or sectorial antennas, which people, they build point-to-point links. Can you imagine just to build a point-to-point of 10 kilometers link between different neighborhoods, right? So, and these are used a lot. So in terms of the network infrastructure, I don't want to go into details, but of course you have a mesh network. So each neighbor is connected with each neighbor. So by connecting to the neighbors, you have a big network which is connected to the backbone of the network, and in this way they are connected to the gateway. And of course, protocols all open source. They are using like Batman protocol as a routing protocol. They are using BMX6. They are using Wi-Fi protocols like that we know. Even they are using TV white spaces as a new technology that this type of networks they know. But of course, it's not just about sharing internet connection. People, they want to share services. And what about these services? This can be a voice over IP telephony, right? I can share peer-to-peer files. I can share game servers. So basically, it's not just sharing your bandwidth, but you are sharing local services. And in a way, this becomes like a how to say, a local ecosystem of services in the network. So imagine I have a game service and I would like to share with my neighbors, so I can put game servers in my node, the whole network will access it. And this makes this network fascinating. But of course, I don't know if there are Spanish, I think Julian is not here. So these type of networks were used in the past, not only for internet connection, but also for politics, right? So for instance, like there was a time when the Catalan referendum for independence happened in Spain, and and it was an online referendum, right? And just 2 days before the election, like voting, the Spain that just blocked the DNS servers and shut down all these type of servers, right? And what happened in that time, in 2017, I remember I was in Barcelona, and that's what they say happened at Tsunami Democratic. So basically, this type of network replicated the servers, and people were able to vote and kind of like work in a nice way. So basically, this was a how to say, like, independent movement of online activism, right? It's not the main intention, but here I'm just telling you why these networks, how this network can be used, and they were used. So this was good. This technology was fascinating, and still it is growing. But well, in 2018 something happened. The MIT Sloan Management Review executive guide, they published a blog or an article saying, talking about 7 technologies remaking the world. And they talk about the augmented reality, they talk about the quantum computers, and in number 3, they say that wireless mesh networks, they will just grow. They will become the great promise for communities that have been viewed as too remote or economically not viable. So this was something like really was the moment of these networks, and this was in 2018. And then if you see how many people are connected in the internet worldwide, you will just see that close to, I was just checking last night the numbers, and it is close to 3.8 billion. 1/3 of the earth is not connected to the internet, mainly Africa, Southeast Asia, some Latin American countries. And maybe these networks can be an alternative solution for these countries. Maybe, let's see. So it was a momentum. Many of these countries, they contacted, and we gave the theoretical, practical knowledge, and we just went to the many African countries to deploy these networks. But there was one thing. Well, this you see in the pictures, you would make 2 tribes to communicate for the first time over voice over IP. You would make like different type of communities for the first time connect to the internet, and this was really fascinating. But one main issue in terms of this type of networks in these countries were that the people were not trained to maintain this network, right? So we needed technical guys, we needed the guys that understand. In most of the cases, the devices would be stolen. And well, so we started like understanding what is an incentive, what can be an incentive, like a motivation for people to keep this network alive. Is there any motivation? Well, yes, and usually the big guys, the big actors would see this. And this was where we were invited from Cambridge University, and I went for postdoctoral studies there. Could we try to kind of like make these networks sustainable by introducing crypto? And this was in 2018, just before the hype of the blockchain that is coming. So the idea was, okay, you are the researchers, you do the algorithm, you code the routing protocol. Can we create kind of like a router for the telecom operators? Just an Uber for telecom. So what is this router? So this router would be something that is multi-frequency. It will work in an unlicensed spectrum. It will be modular. It will have all local services, edge computing, like storage services, like streaming services, and so on. But it will introduce also a very important feature, which is like micropayments. What is this? So micropayment means that if I share my internet connection with you, I'm going to get some money. But how I'm going to get that money? Is it that money or is it a token? So let's see. So the idea was to build the router. So I was working closely on building the routing protocols and in designing. So The idea was like, okay, let's come up with something cheap, super fast, that is affordable, and use all these kind of technologies, and you give to these third countries where they can put and use. So the idea is in 2018, I mean, you can see here, we had the first router operational, and it was in the office, and we just tested, and we just deployed in many countries in Africa to use. So at the heart of the system is the transit pricing. So this is like a solution, this is a brain. So what is this? You have a community network, you have a wireless network, you deploy these routers in users' home, you put some antennas there, and if I'm here a node, and I would like to connect to the internet, I need to go, my traffic needs to be forwarded through your node. Just you, because you forward my traffic, you are going to get tokens, Ethereums. And this is like immutable, something like super sustainable, because I will keep my network alive 24/7 because I'm gonna get tokens. And this was something, well, yes, it can work. So you have the security, fully security digital identity provider. I get my own wallet, and I am getting. And this was something that people use. How does it work in reality? In reality, this is like works. So if I'm in Tetova now and I'm a client and I would like to connect to Pristina, which is like Pristina is acting now as a gateway to connect to internet, my traffic needs to go through Tirana or Skopje. But now Tirana will say, just for forwarding your traffic through our city, we will charge you less, right? For instance, like by charging this amount of money, Tirana is getting money for every gigabytes of data, every gigabytes of data. So now if Tirana decides to increase the price, let's say, of the gigabytes of the incoming and outgoing traffic, let's say it will increase to 180 or let's say 210 maybe cents per gigabyte from 205 to 270. Now this node is not the cheapest one in the network. Now the routing protocol automatically will just forward my traffic through Skopje. So we have a baseline network, we have a micropayments, which is working in Ethereum, and immutable. It's so democratic, so fair, and the system is working. And this was something that it was implemented in the routers. So yeah, maybe you will like this as always, and this was in 2018, and I'm talking this was in 2018 when the price of Bitcoin was $3,000. Can you imagine? So in that time, we did the system, we created the tokens, and we went to an exchange where we reached for a couple of hours $7-8 million of market cap. But the thing is, like, we were hacked. Solidity in smart contracts was super not ready, super not naive, I would say, and we were hacked, and that's why this commercial thing stopped, and we needed to work on defining the smart contract and making more secure and private. Good. And this was like what I did in the last 5, 6, 7 years, and then coming back now to the Balkans. Coming to the Balkans, you already know the challenges, and the idea was like, well, we cannot connect people here because we are already connected. We had 4G, 5G connection, right? We have the telecom operators. You have IPCO, Vala, we have T-Mobile and A1, and well, I mean, we cannot create community networks in the cities. But what we can do is like, can we try to address the environmental issues using these kind of networks? So we had the problem of air pollution, right? Tetova was one of the most polluted cities, topping the charts in Europe. I think it's the same thing in Pristina. So the idea was like how we can tackle this environmental issue using this kind of network. So in Tetova, we have just one air pollution monitoring system, and this is from the Ministry of Environment. So the idea is like, can we do something using this type of networks that will just kind of like give us some power, give us some data to do some edge analytics, machine learning, agentic AI, or whatever solution. So the idea was, okay, so let's try to divide the city and see where people are living and how we can deploy. So what about deploying like this type of community networks, but in a lightweight mode? Instead of using these big antennas, NanoStation M5, M3s, we would just use LoRa, right? So, okay, we have a LoRa. We have a LoRa technology, which can go 2 to 4 kilometers line of sight, fully connected city. So we buy some of the advanced mid-class air pollution sensor, not AliExpress sensors, but of course some mid-class sensors. So we would deploy this in the city, and of course we would just connect this sensor to get the data. And of course, once we connected these sensors and things, and LoRa's were already deployed in the system, we went to the Ministry of Environment, we calibrated them just to say that these are trustful monitors and these are trustful nodes, right? And then we would just go to the city, to the businesses. We would just go to the urban areas, to the rural areas, and just deploy this type of sensors. And here you can see in Tetova, we would just deploy in a couple of locations. And then once you have data, you have 10 sensors, you can do machine learning. And then the PhD students and master students started to do machine learning. Of course, we can predict temperature, humidity. It's easy to do this. But what is challenging to do is like to predict these PM values. Why? Because we have this, what is happening in the Balkans, this hygroscopic effect of humidity coming to the sensors and it killing the numbers, right? So we needed to take to learn a lot of things and also implement in the system. But yes, we would say to people the PM 2.5 is like 100, but what does it mean to be 100? How people would understand 100 PM 2.5? Is it good? Bad? Normal? So the question was like, we wanted to communicate these values which were really high to the audience. But if you communicate them using the academia and academic way of doing, they would not understand. And they still don't understand. So the idea was like, okay, we need some artists here. And we brought, because this project was started by the University of Birmingham in UK, so they stepped in the process. And we said like, they had a mechanism to show the air pollution. So what they call is like communicating air pollution. So can we use these sensors that we have to showcase, to visualize air pollution? Well, yes, there is technology. We are using the same type of ESP32 and Arduinos and stuff, the same kind of like technologies which the students would use. So what would you like how this system will be implemented? It's like this. We would just go in the city center. So we would just take the sensors, the air pollution sensors, which are building this edge. We would just put some air pollution sensors inside and also LED lighting. So if we have more pollution in the air, the LEDs will be lighting off, and we will just take a long exposure shot. So here it's like we are just moving, and we make a long exposure shot, and then at the end of the day, we will see something like this, which is telling us that the air is polluted or not. So if you see more light, the air is super polluted. And at the end, you will see something like this. And this is in the city center of Tetova, where the PM 2.5 was 50 to 60 micrograms per cubic meter. And this was high. And then we started doing this kind of like art photography. Basically, we went to the city center, and here you had like 40 to 50 micrograms. And then we went to the university, right? And then we went to Skopje to see what are the differences. And usually we were doing this kind of like, we were shooting these photos during sunset and during specific hours so that they are much more. And the last picture, like, or photo is more about the smokers. What happens in the cafeterias? This is what is happening. And this was like, can you imagine in a 30-meter square, where 4 people are smoking inside you, the PM 2.0 levels are 500 to 600 micrograms per cubic meter. And this is crazy. I will leave you to judge the respiratory and cardiovascular diseases that can happen because of this, but this is Delhi, this is India, right? And this is happening in our cafeterias all the time. And imagine being exposed to this number of PM 2.5 for 2 hours? That's crazy. So this was a way how we use this edge intelligence and sensors to communicate the air to the audiences. So, to conclude, we need mesh. We needed mesh because it connects people. Yes, we connect people through wireless technologies, connects people through 4G, 5G technologies, but what makes sense that if you use off-the-shelf hardware and open hardware, we can achieve lots of big things. Well, if we have this network, we need to sustain fairness. We need to be democratic, no cheating in the system. So blockchain is definitely the best way to do this. But of course, blockchain is heavy. We need to use some lightweight protocols in order just to bring the sustained fairness. And of course, we need to do some edge analytics at the edge. Nowadays, we have tons of millions of IoT devices. And of course, we need to bring intelligence, not just collecting this data, but at the same time also working on how to bring this intelligence closer to people. So how to bring the intelligence at the edge, not just bringing intelligence at the cloud level where we can do big data analytics. No, we need to do that on the Raspberry Pis. We need to do the edge intelligence in Arduino Unos. And in most of the experiments that you see here, we are using edge devices, Arduinos, and then Raspberry Pis. So I think this is all from my side. If you have any question, please.
Wow, that was truly inspiring. I've learned lots during the presentation. Thank you very much, Menan. Those who are left in the room, anyone have any questions? I guess now you learned blockchain use case in that sense. So we have one question from Arianet here.
Do you see a chance to have a mesh network in the Balkans, in Kosovo, Macedonia? Primarily for science, I would say, but perhaps grow it. What would it take to make that possible?
So if I correctly understood you, how would you make a mesh network in the Balkans? What would it take? Yeah. So the mesh networks, they work on an unlicensed spectrum. So one of the basic idea here is like, it's all about people. We buy the antennas, we buy the equipment. It's not expensive, but we need people to maintain that. And this culture of maintaining this kind of solution existed in Spain, but it does not exist in our case. We can see we have the experience running with our students here in Tetova. We need to maintain this kind of networks. And if you have 10 to 20, 30 sensors, yes, you can maintain it, but up more than that, that's going to be impossible. So if you want to keep alive this network, you need to provide some incentive to people. What is incentive? We cannot provide money, tokens to every, because this is something that you donate for the people's life, right? You donate your temperature data, you donate your PM2 data, which is like very critical, right? So in order to make it sustainable, in our case, academia needs to work really closely with the main stakeholders, the businesses. Can you imagine we cannot put a sensor in the normal cafeterias because they are not allowing us. They would just, they want anonymity, right? So our PhD students are doing PhDs using the data of US. Why we should use the data of US? We do breast cancer detection using the data sets of US. Why? So in our case, like why we need to keep pushing on this, because we need the data. Data is a power. And we need data about our places. We need data about Pristina, because we have ex-Yugoslav factories which are operating and you don't know about the air pollution, right? So these networks are a must, at least for academia at this stage, just to collect this data and provide to PhD students and master students. Otherwise, it's going to be very, very difficult and not interesting and not motivational to work with some country's data. And this is my point.
Thank you. There's one more question over there.
Thank you for the presentation. Does creating a mesh network between, say, Kosovo, North Macedonia, and Albania presuppose or would require a uniform distribution of the population? Like, unfortunately, in Albania, most of the population is clustered around Tirana, and especially the junctions between Kosovo and Albania and North Macedonia are a bit underpopulated. Would that be a hindrance to such a goal, to such a
So
project?
if I understand you correctly, so do we need some kind of specific agreements for creating a mesh network?
No, I
within the
mean
country?
the actual population. Does it require that people are like spread uniformly across a space?
No,
Okay.
that's not the case. I mean, this is mesh network, so we
Thank
can
you.
have a different type of network topologies. We have mesh within the city, but of course, when you just go out in the rural areas, you don't have a proper mesh. But still, we need to have some critical nodes, like with the highest degree centrality nodes that will act as a bridge to route our traffic.
And those would require more maintenance out.
Exactly,
Okay.
exactly.
Thank you.
Exactly. Thank you.
Thank you. All right, so I have an additional question. Is the mesh network still active in Africa?
Yes, they are active. So the idea, the mesh networks are active there, but of course they are trying to find a more lightweight solution for the token payment. Bitcoin, Ethereum, this is not because of the confirmation things that they ask, considering that these networks are limited in terms of bandwidth. So we need some super lightweight, secure protocols for the payment. Still, everybody is using. Once we will be able to pay in Amazon or in Wizz Air using some kind of token, then this will be the reality. But it's very close. Honestly, it's very close.
Good, all right. Big applause again. Thank you very much, Menon.
Thank you very much.
Right now we have a 15-minute break, and then we're going to come back with a lineup